All participants, please kindly check your mic and also your video. Please switch off them both. Hello, Dr. Omid, I cannot hear you. You are speaking, but I'm not able to hear you. Ismail, are you there? Hello. Okay. I think Ismail has done the required thing. Dear participants, please switch off your mic. Dr. Omid, I'm not able to hear you. There is some
I'm
problem.
here. Can you hear me?
Okay, okay, fine.
I'm just muting my micro
Right, fine.
with a button. Okay.
We have about another 3 minutes to go. And exactly at 7 p.m. Indian time, we will start the meeting. Participants, please switch off your videos. Dr. Wamid, shall we start?
Call.
Shall I start with a small introduction?
Yeah, it's
Shall
up to
we
you.
start? Yeah,
I'm ready.
okay. Okay. So, dear participants, welcome to this CMPA series of lectures on how to do it in your clinic. The second lecture in this series is titled Radiochromic Film Dosimetry and will be presented by Dr. Wamid Abdul Rahman, who is a fellow of Canadian College of Physicists in Medicine and also American Board Certified. I'm happy to introduce him. He is the Chief Medical Physicist and a Senior Consultant in Medical Physics at the King Fahd Specialist Hospital, Dammam in Saudi Arabia. I have had the privilege of working under him for about 3.5 years when I was working in Saudi Arabia. He is an excellent medical physics teacher and probably the best physicist that I have ever worked with.
That's too much.
He will be now presenting on radiochromic film dosimetry. Dr. Wamid, please.
Okay, it's a pleasure to actually to participate in this series. I mean, my colleagues in India, they allowed me to participate in their conferences, and now participating in remote lecturing. This is really an honor for me. So today I'm going to talk about GafChromic dosimetry. Just to make things clear, I'm not an expert in this field, using it for real research and so on. But I will show you how we actually use GafChromic film for simple things in our department. So I'll just share my presentation. Okay. And desktop too. Okay. Okay, so my slide is clear, Dr. Ganesh?
Yeah, we can see that.
Okay. So I won't go into a lot of details on GafChromic films and how they're made and their properties, but I will show you, and this is what Dr. Ganesh asked me to do, is to show you, clinically how we use such films. So I'll show you 3 specific applications at our institution. We have used films for commissioning of IMRT and VMAT techniques for Clinac 2300 CD and true beam machines using TG, AAPM TG119. I also had the privilege of having a student, a master degree student, where we had a project on conducting portal dosimetry and Linac outputs, postal, sorry, it's not portal dosimetry, postal dosimetry. It's postal dosimetry and Linac output auditing. And one of the other applications in our clinic that we use films for is TBI irradiation or in vivo dosimetry. So the basic of GafChromic EBT3 films, it's basically a radiochromic film consisting of a single layer of radiation-sensitive organic microcrystal monomer. So please don't ask me what that means, okay? I'm just reading out. But It actually went through a lot of development. There was EBT and then EBT2, EBT3. The nice thing of EBT3 is that the active layer is sandwiched like in between the two polyester layers, so really dead middle. EBT2 I think had 2 layers, and that caused a bit of problems in terms of resolution when you want to scan the dose. And EBT1 actually had 1 layer, it wasn't centered. But this is EBT3. I'm not sure if there is actually a new breed of GafChromic films that is out. Probably there is. So basically, the dosimetry with GafChromic film is okay. When you irradiate a film, then the film becomes darker, and this darkness increases with absorbed dose. The nice thing about the films is that you don't really require processing on the film. It's self-processing or self-developing. You just leave it after you irradiate for some time, and then the darkness, you'll see the darkness there. But they do have some advantages. For example, is that for very low doses, I think they're not really good. You cannot rely on them. And probably, as I will explain, the TBI is that you probably need to wait for some time if you want to have good results. You cannot immediately scan the films after the radiation. And basic idea is, you get the signal of dosimetric film is just a transmission measurement. So you sandwich the film, you have a light source, and you have a sensitometer that reads the intensity of the light. So this intensity is going to decrease based on the darkness of the film. The darker the film, the lesser the intensity is going to be read by the sensitometer. So for all our readings, we use a scanner, Epson 10,000. I think there is a 12,000 scanner model now. We scan everything in transmission mode. This is important, especially if you're looking for resolution, you're looking for spatial resolution. But you can actually, if for many of the applications, maybe you could also scan it with the reflection mode, if spatial resolution is not really a big concern. 300 dpi, dots per pixel, dots per inch, sorry. That's the resolution we use. And that's why we like this scanner. It's a 48-bit RGB. Regular scanners, which are 24-bit, they will give you they probably have a dose resolution of about 5 centigrades. So you will know your dose within 5 centigrades. Clinical doses, I'm talking about like 2 grays, 3 grays, in that range. The dose resolution is, you cannot know the dose better than plus or minus, or within 5 centigrades. But with the 48-bit scanners, the dose resolution is actually better than that. I think it's about 0.2 centigrade or even less. So the films, we cut them in small pieces of 2 by 3 centimeters or 2 by 2.5, and we just shoot the films in a solid water phantom. We place the film at Dmax, and we give it a known dose. So we do this for many pieces. So now we're talking about how to calibrate the film, use it as a dosimeter. And I will talk to you now about the first project that we have used films for, is the commissioning of IMRT and VMAT. Now, the film calibration, of course, the procedure is you shoot the film, these pieces of films, and give them specific dose, known doses. And then we were using a commercial application that's required to carry out the gamma analysis. So we scan the films and import the images, this image into the application. And then when I calibrate, it has a module for film calibration. Then I will go and highlight or select a specific region of interest in this film, for example, and I will specify the dose was, for example, 20 centigrades. This region was 30 or 40, and so on. But and then it has something internally that constructs its own calibration curve. We really don't have control over that. So establishes that, and it's the dose response curve for the film. And what we do, just to make sure that everything is fine, is we make another scan or different small pieces where we know the doses and scan them and send the images to the application and ask the application, okay, what is the dose actually received in these pieces of films? So that's how we validate our calibration. We have used it for validation of TG119 and also for VMAT cases. But basically, that's our first application. And the point I want to make is, is that we really did not know how did this calibration curve look like and so on. So this is not interesting for the talk, but just an application of the films. The next second application is TBI in vivo dosimetry. This is where we're starting to, okay, maybe we do a little bit better or more understanding of this calibration of the films. So this is how we commissioned our TBI. That was done in 2011. Here is Dr. Ganesh. He was a great help in doing this job. And eventually, we actually established this technique where the patient is placed in a box, and we fill this box with rice bags. So we're converting this patient essentially to just like a box. Okay, so that's how we do our TBI. So this is another image, another view of the patient inside here, and we're just putting TBI box. We're putting rice bags to fill this box. So we wanted to do in vivo dosimetry while the patient is being irradiated. So we use a chamber. This chamber is positioned between the patient's thighs. So we put this chamber is probably here. And then initially when we started this project, we were using TLDs at 11 positions, not 15, 11. So as indicated here by the figure. But of course, with TLDs, we hate doing dosimetry with TLDs because they require time. You have to leave them for some time so that those peaks at room temperature, they don't affect the dosimetry. So we switched to MOSFETs where we get the reading on the spot. But then, unfortunately, our MOSFET kits, something happened, they got damaged, and we were stuck. So we had to come up with a different in vivo dosimeter. And what do we have? We have GafChromic films. So we have been using that since 2015. Actually, today we don't use films for in vivo dosimetry for TBI. So again, the calibration is the same thing. You shoot the films with the known doses, and then we use this software, ImageJ software, because the dosimetry with GafChromic film, we need to actually do it with the red channel, and I will show you actually this in a moment. Probably the software that we were using to do the commissioning for the IMRT and VMAT, probably it was decomposing the channels, but really I cannot tell. I really don't know. But at the end, when we tested it, the dose, I mean, it was doing a good job. Okay, and so basically we read, so we scan the films prior to irradiation, and then we scan the films after we give them. So this is the calibration process. Okay, after we scan them with known doses, and we have this equation. We calculate what's called an optical density, and we use the ImageJ. So all the dosimetric data, we use it actually just from the red channel. So we decompose. This is the film. The film is decomposed into red, green, and blue colors, and the dosimetry is done only using the red color. So this is here an example why we're using the red channel. This is the response or the optical density for the blue channel as a function of dose. And you see that this optical density, almost its background, it's not sensitive to the dose. But the red channel, actually within the dose range that we're interested in, so we're interested in something about 2 grays, the red channel was actually the best of the three channels to do dosimetry. If you're interested in doing higher doses, maybe I don't know what's the range, but probably around 10 grays, then this red channel would actually saturate at these doses, and probably you're stuck. You have to do the dosimetry with the green channel because you will see still there is some response there. So this is why we were using the red channel. I think for clinical doses in radiotherapy, even up to 1,000 grays, probably the red channel is the one to use. So once we scan the film, then we, with ImageJ, we actually define a region of interest, 5 regions of interest. And with ImageJ, it actually gives us the average color intensity within that region of interest. So we take these 5, we calculate the standard deviation. If we're interested for finer, like reporting doses with uncertainties also. But in TBI, we were not interested in defining uncertainties of doses that we measure. So here is an example. So here are the films. These are the doses, given known doses. These are the backgrounds. So you could, for example, just take an average, or even you don't need to read the background for each individual film. You can just have a small piece where the dose is 0, and then you have one image, you scan it, and you take the reading from that film to be your background. Because if I take an average of background from the film, it's roughly within 0.7%. So that's fine. These are the intensity or red channel intensities as a function of those, and we calculate the optical density. We put this in a Excel, for example, and this is how the optical density, or the dose actually as a function function of optical density looks like. And we just do a polynomial fitting, a very simple polynomial fitting, this equation. And essentially for TBI, most of the doses are just going to be here. So even if we have a problem in the fitting in this region, it's fine. But it's important that within the 2 gray region, that we have a good fit there. And we place those films. I'm going to show you actually after the presentation how we do this. I will open the camera and show you. So after this TBI, these are 6 fractions. So with the chamber, these are the chamber readings for the 6 fractions with an average of 207. And these are the dose obtained with film dosimetry at these 11 locations. So at least 9, that is probably position 9 is very close or at the patient, at the chamber level, and we see a very good agreement at least between these 2. These are higher because they are more in the lateral direction of the patient. So that's our second project, how we use TBI. The third one was actually a more exciting one. It's doing postal dosimetry auditing with a student. So we were not using just simple Excel because now we really wanted to actually, when we do the fit, we wanted the parameters with uncertainties to really do some appropriate dosimetry there. So we had to build our own in-house graphical user interface program, and with the Zojo software. So basically these points here, they represent the dose. This is dose, and this is the optical density, and this is the line fit equation with I think 3 parameters, and then we do something fancy to calculate what is the uncertainty of these parameters. So at the end, if we want to report the uncertainty in the dose when we do the postal auditing. So okay. So at that time, we looked at the literature, and there were a few equations. I think there are even more today. This project, I think, was 2014. So this was a very common equation used to fit EBT3 films. B is a constant. This is the optical density. You have another constant C, and then this power. some papers actually fixed it. So it's a power of 3. Some used a 2, and some even actually allowed it to be part of the fitting itself. So it's a variable quantity. So this is the red, and again, this is the calibration curve for ABT3 film, this 6MV. And at that time, we did this calibration curve, calibration of the films using 6 and 15, 6, 15, and 18 MVs. We used, I think, 5 different energies. So we 6, 15, and 18. So there were 3 beams with 6 MV, 2 with 15, and 2 with 18. One of the big advantages, nice advantages for GafChromic films, is that it's energy, almost energy independent in the mega voltage range. And that's why we wanted to use it for this project. But we wanted to show that it is actually energy independent. So these are the, this is, for example, one results of the fitting when N was equal to 2. So this represents the calibration, the parameters used by fitting data from, let's say, 6 MV. This is from 10, 15, and 18, and so on. So because the parameters are roughly constant, that's why one could say, look, yeah, probably these films are really energy independent. So this is for a, I think we had 2 batches. So this is also one important thing for film, GafChromic film dosimetry, is that in each box, for each box, you will find a serial number or a batch number. So the assumption is that this film, they were cut from one large piece. And if you calibrate, if you establish a calibration curve, that should be usable for all film dosimetry used for that box, that batch. But if you have a different box, then you need to establish a different or its own calibration curve. So this is for one batch, and this was for another batch. This is when N equals to 3. Again, we did the fit with the program. And this is when N, I think, was variable. So there are a few, like outliers and so on, but at the end, they really don't really matter in the dosimetry itself. Because so here, for example, these are the coefficients. So this is the one coefficient, this is another coefficient, and so on. Okay. So at the end, we got this table for the different, the coefficients depending on the fitting model that we're going to use, where we have established also uncertainties for these coefficients. And that was the whole point of this, doing this fit with our own application. There are probably available commercial applications, but we did not have it at that time. This is the Phantom, Postal Phantom. It's just a small piece. I think it's almost about 20 centimeters. So the film, there is a small, let's say, engraved part here. We put the film here, and the top one, we lock the film in position. And then we just put this box at a given, let's say, 100 SSD, and shoot, radiate the film, and then we read the film. So this Phantom is used now to conduct the Postal dosimetry part, not the calibration part. The calibration was done in full scattering conditions with the solid water. And at the end, so after we did this experiment or project, then we went and monitored or just ask our colleagues, friends, just shoot, report the dose to the film, and let's see, is the reading confirming what you think you're delivering or not? And we get a very reasonable or desirable agreement. So we just showed in this project that actually GafChromic films could be used as postal dosimeters. So in conclusion, GafChromic ABT3 film is a practical dosimeter to be used for dose validation in the megavoltage beams. The EBT3 film exhibits a negligible energy dependence, but on the other hand, they are not linear dosimeters. So if you want to use them, it depends on the application you're looking at. If, for example, you're doing a sort of a TBI where the dose, you're measuring doses that are roughly around 2 grays, then you can have, even if you use the straight line fit in that region of data, I don't think that's really a terrible, that is terrible. That's also okay. And so at the end, using them for Postal, as Postal Phantom were very satisfactory, and for in general dosimetry applications in the mega voltage photon and electron beams. So let me just show you a little bit of, this is a, since this is a show and tell application, let me just close this. So this is ImageJ. It's an application you can download actually free. It's free. And let me load one, let's say the calibration. So here is, for example, this is a film. Okay, so we cut these pieces, small 2x3. We shoot them with known doses. So with ImageJ, if you go here to image, and I think under color, you can split the channels. Then ImageJ is actually going. Is it visible, Ganesh, what I'm doing?
Yeah,
can
yeah.
you see this?
Yeah,
okay.
We can see.
Okay, so this is the red channel. Okay, so that's the red, green, and blue. Of course, the blue one, that's useless. Although there are some applications, I think that there are some researchers can actually use this, the signal of the blue channel, to do some corrections. And so once I'm here, then we can do an analyze. So we measure. Okay, and then I can go and select, okay, what is the dose? So I think Control M. I will just show you the, okay, it's here. Okay. Okay, so once I select, for example, this region of interest, and then I think Control M, then the reading, this is the reading. So this is, for example, number one was the first reading, the region of interest here, and then the number two is one here. And we do this for 5 different regions of interest. And we take, this is the mean intensity, color intensity, red. So we do this 5 regions, and we take these signals and we average them to get the uncertainties. So so we take the average as the signal and the standard deviation as a measure of the uncertainties there. So if I select, for example, this region here, this is 10, we expect, because it's darker, you see the signal is actually, now it's 21,000. Here it was under 38, 39,000, 39,000. So the intensity, or the color intensity, actually is lower, as so this is more red, right? So here probably this signal is even the highest if we do that. This is actually 65, this is 65-bit colors. So this has the highest intensity, but there is always, the film always there is some intensity attenuation within the film, and that's why you need to calculate the optical density. You need to measure the background and then measure the signal with the dose and obtain your optical density. So this is how we were doing it manually. It's tedious, but the nice thing is, once you have done it for a batch of films, then a batch of film has 25 large pieces of films. So you can use them for a year or two. Sometimes maybe we can actually check this calibration because if the films were, for example, exposed to ultraviolet light, I heard that they might it might affect the dosimetry of the film. So every year and so we do actually establish these curves. I'm going to switch to my camera just to show you some other stuff. Just give me a minute.
We cannot hear you.
Okay, so can you hear me now?
Yeah.
Okay, I had it somewhere here. Okay, so this is, for example, although this is a larger piece of the film. I had them here anyway. So this is a large piece of film, and what we do, we wrap it. So although I'm now touching it with my hands, but when we do the dosimetry, we use them for dosimetry. We try not to either wear gloves because we don't want, the oil to be oily and so on, because that can affect the dosimetry part. So we usually handle them very carefully. And what we do is I try because the films are sensitive to the orientation, how you scan them in your scanner. So for example, if I scan the film in this direction or in this direction, then the signal is going to change. But a few days ago, my colleague Saad Dilejan, he told me actually this issue has been fixed. So in the past, we used to actually take a lot of care in how we're going to scan the films. And that's why purposely I made actually this dimension longer than this. So the film comes, this is how a film looks like. So I make sure when I cut that, okay, it's like that. So at least when I do the calibration, and I know I'm scanning, and this corresponds always to the large side of the film. And this is how we put it in the scanner. So we will put the longer side parallel to the longer side of the scanner. This is just to make sure that we're doing things in a consistent way. This is our phantom. So this is the one that we used for our project. So you see, here is where we placed a film. Trying to find. Okay, I don't know where is that piece of film now, but usually, so the film, we will place it here, and then this piece, we can place it on top of it. This is about 20 centimeters. The film was positioned at a depth of 9 point, I forgot, 9.3 or 9.4. Originally, we wanted it to be done at 10 centimeters. That's what everyone uses, but the machinist who designed this or who shaped this, he got the dimensions wrong, and we said, okay, it's fine. So we did this corrections with Monte Carlo. We knew how to do that. Now for the patient, so that's that piece of film. So what we usually do is for this small piece of film, we try to wrap it with a piece of paper. And we will actually use some tape. And outside, I will put, for example, this goes to position 7, position 8. That's for TBI dosimetry. Because remember, these are going to be placed in contact with the patient. So I don't want the skin, the oil from the skin, to affect the film. So we will put them around a piece of paper, and then we wrap it with tape so this piece of paper does not open. And we give it to our therapist. They know the positions, they put those films. And at the end, when the treatment is done, we get the films and we wait. I think we wait for 4 or 6 hours. This is something very important to do proper dosimetry. And you need to be consistent because you need to give the film time to self-develop. Some papers, they show actually you need to at least 48 or 24 or 48 hours. But we cannot afford that in TBI. Usually the physicians, they want the results immediately, and that's one of the disadvantages that's one of the disadvantages. We have, sorry, my, my son came, interrupted me. Okay, so that's one of the disadvantages actually for film dosimetry, is that you need to wait for some time. You cannot actually produce the results immediately. So I hope I've given you some idea of how we use these films in our clinic. Definitely, even the way, I mean, I think we could actually improve on the way we're doing it. For example, I've heard some centers, in order to reduce the background signal, what we do is we just put the films directly on the scanner, and after that, we take the reading. Some centers, they actually use some black sheets, wrap the scanner with that, so that no light from outside goes inside the scanner and affects the signal. They think when you do that, your background can actually be reduced, will be better. We don't do that, but maybe if for an application where the dose needs to be known more accurately, and that is really an important problem, maybe then you should take this into considerations. So I'm going to stop now, and I'm willing to have questions or discussion on this matter. Thank you very much.
Thank you, Dr. Omid. And yes, there are some questions. Can I start with the questions?
Yeah, go ahead. I finished.
Yeah.
So, okay.
Fine. Right. Like the first question is that what increments, that is the dose increments that in those films, 1 to 16 films. So what were the increments, and up to which upper limit the dose calibration is done?
Okay, that depends on your application. Okay, so for example, in TBI, we do doses up to, for example, 2 grays, right? So probably I want to calibrate the films up to 3 grays, maybe 4 grays, okay? So I will use, for example, 25 centigrades, but very close, or maybe steps of 50 centigrades, but closer to the region of my interest, I will actually take more points. So I will do, for example, 170, 180, 190, 200, 210, like this. There is no limit because you're doing a fitting. Now, if you're doing something, let's say, if you're going to use film for higher doses, then definitely you need to calibrate the films, establish the curves up to above, the value that you're interested in. You could actually do even finer. So, for example, if you're going to 1,000 centigrades, you can do films step of 25. There is no problem with that. It's more points, better fitting, and so on. But we try to, we choose not to do that. We try to actually expose different dose levels near the doses that we're interested in.
Okay. The other question is that, do you use any kind of cling for film for handling? I mean, what kind of equipment? How do you handle the film? Just hold it by the fingertips, or any other?
For example, we use gloves first of all, okay, because you need to cut. It's not just about tweezers and not, because the films, they come with a large piece. Now, if you want to cut them into smaller pieces, okay, you need to handle them properly. So we use gloves. So these are available in the clinic, I'm sure. And then those small pieces, you can try to, for example, hold them from the side, not in the middle. Maybe if you can use clamps or tweezers or something like this. So it's like TLDs. TLDs, no one would recommend that you actually carry them with your hands. You use, something to pick them up. And usually for TLDs, it's better it's a metallic piece, because if they're hot and you have those plastic tweezers, then they can melt a little bit, and that will affect the TLD.
Okay. So another interesting question, choosing signal from the red channel, is it done during the scanning of the film, or is it done at the time of analysis with the ImageJ?
Well, the scanner will scan all colors, all channels, red, green, and blue. And one thing, when you save the image from the scanner, don't save compressed images. So use a TIFF format. The images are not compressed. So don't go and save JPEG, for example. JPEG is compressed. Save uncompressed images. That's TIFF. For the ImageJ, the scanner, they will give you an image. An image, they have all colors, red, green, and blue. So the ImageJ, we use ImageJ for two reasons. First thing is we can split the channels, split the colors. And then we just get the red channel, like this one, and then we start to read the regions of interest in the films. And as you notice, I marked the films when I exposed them. I wrote down what doses was given to film number 1, 2, 3, 4, and so on. So because they will appear in the film and in the picture, in the image, and then I know this is actually number 1, the dose is so on and so on. One thing I did not mention for the calibration part is we actually take an output of the machine just prior to calibrating the film. So we account for output variations on our Linux.
Yeah. The next question pertains to this particular screen only. So please don't change the screen. Like here we see the film pieces 1, 2, 3, 4, 5, 6 like that. Now suddenly, if you look at that, film piece number 12, 13, 14 are much darker than 15 and 16. So there is a question that why this 12, 13, 14 are much darker than 15 and 16.
Yeah, probably when I've done this, I exposed or irradiated the films up to 15, up to 13, 14. 15, I did not probably irradiate, or it was something in between. And 60. So I mean, don't think this might not be sequential. I might, for example, give him 15, like I was doing the experiment, and then I said, okay, I have 2 more films to actually spare. Maybe I'm going to do another one, maybe at a dose of 180 or 160, for example. So this might be it. Okay. Is it clear?
Yeah. Got it. So it's not necessarily that it is in the order of.
Exactly. I could, for example, shoot number 1, 300 centigrades, number 2 to be 0. I use it as a background, 3 something else. As long as I record that and I know which film got which dose, that's not a problem. Yeah.
Right. Now, another question, interesting question. Do we need any build-up at the time of using the film for TBA in vivo dosimetry? Well, like you covered it on the paper, but when you place it, do you put any build-up?
We don't, because our TBI, the patient is actually sandwiched in these fried bags, okay? This might actually, for example, let me show you again the results of our TBI. With film, because that's an interesting question, I mean, okay, so these are the results. For example, number 1, position 1, you see, I'm always getting high doses. And this is position 1. If we look at here, this is actually just above the eyes. And for the patient, I don't think there is even any bonusing there. So that's why it's, I mean, yes, we expect the dose to be higher. But for example, position 4, position 5, we expect the doses there to be higher to those in midline. Let's go back to the table. Okay, not this one. Yeah. So 4 and 5, yes, they're usually higher than, those in the midline. We know the reason. We don't put bolus above them. We assume that the rice bags, they will do the job. But maybe that's could improve the reasons. One of the issues, okay, since these films are really, you cannot use them for example, on a patient with photon beams, placing the film on the skin without any buildup, because then the dose is going to be very low. It will not confirm anything. For electrons, maybe there is no problem. But films, they cannot be used, I think, should not be used for low dose measurements. Even for another example would be if you want to use the films to measure, for example, gonad doses, where you have them shielded. I think the signal is going to be low, but what is the dose? There is a large uncertainty in the dose that you're going to measure with films. So I wouldn't recommend using films to measure under shielding, for example, or at the skin for photon beams. But if it's like what we do on TBI, then I think that's not a problem.
So there is another question regarding SRS and SRT. So the question is whether it can be used for SRS and SRT QA because it is not linear at high dose.
Well, I think first, if you want to do you probably need a software for that, because you're not looking just at the dose. You're looking at, even how the profiles look like and so on. So with our crude method with these films, when we cut them, that's just to get a point dose. That's not a problem. But and there are probably commercial software, and you just have to follow what the software recommends. What do they want, and so on. So I cannot comment on this. I haven't done it for small fields. I've used, usually with the IMRT, but small fields I haven't done. But I would think with small fields, you're interested also on the profiles. So then spatial resolution is an issue. So that is something when you use the software, you have to think about that too, to do dosimetry with it.
Is there any other scanner suitable apart from this Epson 10,000 XL series? The latest one is 12,000. So the question is that apart from this Epson 10,000 or 12,000, so is there any other scanner that is suitable for this type of application?
I haven't actually searched that particular point because we have this scanner. We were not actually looking around for another scanner. Okay, this scanner is a bit expensive. And I know some people actually trying to find other scanners, other types, and so on. The point, or if you can't find one, of course, you should share this information with all of us, especially if the price is lower than this Epson scanner. But look for the following things. Look for a 48-bit scanner, and look for a scanner that I think you can have 300. I think most scanners can actually save images with those resolutions. But look for a 48-bit scanner, because the 24-bit scanners, that's already a 5 centigrades uncertainty of whatever you're going to measure.
The next question is regarding the T-set. So we use films. The questioner asked, they are using films for T-set in vivo dosimetry. So is it advisable to wrap a paper around the film in the case of T-set also?
Well, okay, that is a bit tricky. I don't know, for example, when you put this piece of paper, how much of the dose is going to actually reduce, on the other side. Maybe if that is not a lot, I'm not sure. Maybe just not, 1 millimeter, maybe it's not a big deal. But I'm really not sure. But if the dose is not really reduced a lot behind the film with the piece of paper, then that should be okay. I haven't done it. I really don't know. I really don't know about this question, but that would be my concern. Especially because we want to treat the skin with a given dose. How much does this film reduce the dose when it's placed on the skin? I really don't know.
Then there is another question. I'm not sure that what exactly it is. Do you do any white light sensitivity across the scanner that needs to be corrected?
I don't. Okay, and I don't mean that it's not necessary. This is what we try to do is, okay, we scan at the same region, region. We place the films, and okay, probably it's on one corner, and we try to place the films out there exposed roughly in that region. Now, if you want to do a better job, yes, maybe it should be corrected for. I'm not an expert on this field. You could, for example, test your scanner. Test and take a piece of film and place it on different locations in the scanner and see what the values you're getting. And if they are roughly the same, then no correction is needed. But if there is a correction needed, that would be a nightmare, because now you have to assign a correction factor for each region in the scanner. I would suggest just get a new scanner.
Yes, yes. Another practical question: how to remove fingerprints while cutting, and what method is recommended? How about using multi-channel instead of single-channel red?
Multi-channel? Okay.
Yeah, the first question is about how to avoid the fingerprints. Second question is about, instead of using the single red channel, what about using multi-channel?
Like for the first question, okay, we try to touch the films with gloves. If suppose the films are small, and you can have plenty. So a single sheet, you can get like 150 small pieces of film. Okay, so if you touched one and you cannot remove, with a cloth or something, just don't use it. Just take another piece. So that would be my advice for that. If you have wear gloves, try not to contaminate your film. But if it got contaminated, the problem is if it got contaminated after you expose them, that would be an issue, especially if this was done actually on the patient. That would be a problem. So you have to be a bit careful about how to handle films in order that you don't fall. And I really don't know what sort of material. I usually would just take a piece of tissue napkin and just try to, if this happens, I would try to remove this grease from there. The second question about using different, you could have no problems with that. We don't. It's just too much work. But for example, basically you want to actually do for example, dosimetry based on these two channels. You could do that. You could establish a calibration curve for the green and the red, another one for the red. Once you scan, you get the dose from the green and the dose from the red, and maybe take an average of the both, or they should confirm one another. You could, I wouldn't say no. But if you're going to higher doses, like in the 10 grays or above 5, I think you would then this will become not as sensitive as it is here in this region. It saturates. But the green, you can use that. That would be probably a better. And remember also, this has a higher sensitivity than the green channel. What I mean by that is, for a small change in dose, you have a higher change in the optical density for the red channel in this region compared to the green region. So if you establish your uncertainties and so on, yes, I think you can.
We have more questions, so let me see which are the most important ones and I will just put them across. What is your experience about small field dosimetry? Have you done any small field dosimetry using these films?
Not yet. Not yet.
Another practical question, 300 dpi results in too many unrealistic spikes within even uniformly irradiated film.
True. And that is why we don't, for example, I don't take the standard deviation, let's say, okay, let's open ImageJ, let's take a reading. I'll just show an example. So let's take this region here. Okay, and let's look at the measurement. Okay, measure. Okay, so the question is basically, why don't I take this standard deviation? This standard deviation is actually the standard deviation of the pixel values of within this region. Yes, I agree. And that is why, because there are a lot of spikes, that's why we don't do this. We want to reduce our uncertainty. So instead, what we do, we will actually do a region like this. Okay, this is region 1, 2, 3, 4, and 5, and only take this signal, the mean, the average signal. And from these 5 readings, we calculate the standard deviation.
Okay. You mentioned that the orientation dependency of the films can be fixed. So how are they fixed?
No, they're not fixed. They are sensitive, okay? Or the dosimetry depends on that. I think I heard just a week ago from my colleague, Saad Dilejan. He's finishing his PhD and his work has been doing everything with GafChromic films. I don't think he knows how to hold the chamber. He will know actually, good dosimetry with films. But and he told me that actually this issue of film or scanning orientation has been fixed for films, because that used to be a big disadvantage, and one has to be very cautious, handling, making sure the orientation is you're consistent with scanning orientation. You cannot, for example, scan. Suppose you're doing the calibration, okay? I cannot scan some films, in this direction and the others in this direction, okay? Because the backgrounds are going to be different and the signal is going to be different. So we have to be consistent. So my recommendation, if you have an old batch of GafChromic films, I think you just have to be careful with this orientation. If you don't know, just test it, scan a film, and take an image, rotate it 90 degrees and scan again and see, are the signals different or not. I heard you can get up to 5-7% difference in signal between the two orientations.
So another very interesting question, why the response of the film is different when exposed to 4 gray in a single shot versus 4 times 1 gray?
That I have not investigated. I haven't done such a thing.
Then the other question is that, is it possible to use a GafChromic film for SRS SBR TQA? I mean, dose is around 25 gray. And at the same time, can we analyze the film for low dose regions accurately? That is, say, like around 2.5 centigrade or around that, approximately 1% of the maximum value.
So you're saying about 2,500 gray, 2,500 centigrades, right?
Yeah.
Okay. I personally have not done it. We don't have a stereotactic program yet in our department. But my suggestion is you do the calibration. Okay. So you do it and then you tell us, can it be done or not? I think it can be done, because even if the red channel saturates, the green channel is also going to be available. Now, if you, at these high doses, you want to also get accurate measurements at very low doses, I think you're asking too much from the films, but maybe I'm mistaken there. Maybe it's possible, but I think usually at low doses, films are there is a larger uncertainty there.
So there are many more questions. As I'll just take only important ones. What is the total uncertainty associated with this work on TBI, like machine output, scanning position, and positional uncertainty in the patient?
Well, this you can estimate from, just have an estimation from, let's bring that up. Okay. Uncertainty, well, I really cannot tell. I will just take an average of these data. And in TBI, we usually want to deliver the dose to within plus or minus 10%. So for example, everything here is fine. This is just at the edge of 10%, these three readings, but these are at, at the armpits where the dose is actually a bit higher, because of the dosimetry part. These are here are around the neck, okay, and they look fine. Now, why they're higher? Because probably the packing, we use rice, and maybe that the rice do not attenuate the beam like water. It's a bit less because there is some air in the rice. When we did the dosimetry, we did it like for TBI. You see, we used actually solid water. So the rice might have an effect. It's not attenuating the beam as solid water. I've tried to talk to our physicians about this issue and was suggesting, look, maybe you should lower your prescription, maybe to 190 or 180, so that at least now, or 190, for example, so at least we know you still want 2 grays. So the dose that the patient is going to receive is going to be plus or minus 10%. Now, 2 grades is actually our lower point. So everything is going to be higher than that. So if, for example, they lower their prescription to 180, for example, then we will guarantee that the dose in the patient is going to be between 220 and let's say 180, which is within plus or minus 10% of the 2 grades that they wanted. But they did not want that. And they said, we're fine. We just want the 2 grades. So that might be the reason. The uncertainties, a lot of factors in it, not on the dosimetry part, but also on the bolusing, how this is placed. And sometimes in one fraction, there could be, 2 pieces or 2 bags could be actually not positioned properly. So there is less attenuation. That's why the film getting more dose and so on. By the way, the results for MOSFETs were very similar. Okay, so it's not like it was much better. Were very similar. So this tells me that it's about the packing, the rice bags.
How about scanning of the unexposed film, exposed film of known dose, and the actual dose, unknown dose film, all at the same time? Can it be done, or we have to do separately?
No, you can. I think you can. So basically, who asked me about those 15? Okay, 15, and where is that film? Okay, yeah, I think I know. Okay, so here, for example, you could, for example, put number 17, which is not actually exposed, 0. The reason is, at the beginning, when we started doing our work, we used to put the films unexposed, and we take the background from each one of them. But as I showed you here, for example, where is? So this is an example. This is in this data. I've taken the background for each individual film. Okay, but you could actually take a background of the average of these, or one of them, and they, all of them will be within 0.7%. Okay, so you can, for example, take one scan where one of the films is unexposed and the rest are exposed. I don't think there is a problem. Maybe the uncertainty is going to be a little bit higher, but maybe not really a big deal.
Large scanner for scanning film causes trail light effect. I think this question, same thing. Do you recommend Epson scanner for small size films?
I have no idea. Okay, I have been using them, like these small films. I did not face any problems. The films should not be too small, also, because the cutting. This is also like here, for example. I would not take any signal within very close to the edge of the film. I try to take the region of interest inside. So if your films are becoming smaller and smaller, then you will have a limit on the size of this region of interest. And let's see if I think ImageJ also shows you the area of the region of interest. So I think this is the area. I don't know the units. Is it in centimeter squared? Probably yes, it's in centimeter squared. So it shows you, the area of the region of interest. But this is how we do it. We did not have any problems. At least for the applications that we use films for, we're very happy with the results.
I think those are the questions. The other questions, more or less, you have already addressed almost all of them. There are some few more, but I think you have covered them.
Okay.
So I think if there are no more questions, thank you very much, Dr. Wamid, for an excellent presentation. We look forward to hearing you more in the months to come.
Yeah. Well, thank you very much. I really, enjoyed this participation. As usual, I really enjoy dealing with my colleague physicists from India. I see Paul Ravindram is there. Some others. Hola, Dr. Hall also is there.
Yeah.
So, I mean, Saju is there also. So anyway, so I'm open to any. I would like to share any clinical thing that we do. I'm not an expert on GafChromic film dosimetry in the level that does the scanner affect this type of scanner or the sizes and so on. But I'm showing you how we're using it clinically. And if I was not satisfied with the results that I was getting from the film, definitely I would not actually use them for any clinical applications. But I would encourage those who are more expert than me in this field to actually maybe present some of their work, and especially because a lot of the questions are about small field dosimetry, and that might be an interesting topic. Also, maybe you can accommodate in these lectures.
So thank you once again, and Secretary Dr. Paul Ravindran also would like to convey thanks to you and also to all the participants. Participants, once again, thank you very much, and please look forward to more interesting lectures in this particular series. Another one will be coming up in about 3 weeks' time from now. Thank you very much once again to all of you for joining.
Okay, thank you very much, and good night to everyone.
Yeah, night.